Vertex cells, they are diploid. So they come from diploid cells. But and red blood cells, they don't divide obviously after they, because they don't have any. Yeah. They have a limited lifespan of like 3 months, and then new cells are made. Okay. Well, continuously, it's already every day. You know, you're losing the old ones and new ones are made. But they don't have a nucleus. So I'll have to see. Let me do the search of the literature, see what category they are in. But they're not gametes, so they must be somatic cells. There's also the platelets, which are parts of the cells. They're not actually cells, parts of cells. Maybe red blood cells fit into that category because they're missing the nucleus. I don't know.
Yeah, maybe, yeah.
What's happening with this computer? So today we're going to continue and look at meiosis, how it produces the gametes. Okay. So meiosis, we will find that there are some similar steps, but there's also different steps involved in meiosis to give rise to gametes, so sperm and egg.
That meiosis.
So yeah, we finished. Did we finish yesterday's lesson?
Yes.
Yes.
We'll probably show the dean the videos of Assortment.
Yeah. Okay, here we go. All right, so in meiosis, there's actually 2 cell divisions. Okay, so remember, mitosis has 1 cell division. We get identical daughter cells, which are diploid. In meiosis, we get 4 cells in the 2 divisions. Okay, non-identical, and they are haploid. They have half the number of chromosomes. So in meiosis 1, so it's actually divided into 2 divisions. So we call it meiosis 1 and meiosis 2. We still have these, you know, the prophase, metaphase, anaphase, and telophase in cytokinesis. Steps are the same. You get DNA duplication in the S phase. So before meiosis 1, there is duplication of the DNA. However, remember that in metaphase, we got the, in mitosis, all 46 chromosomes line up in the equator.
Yeah.
In meiosis 1, the 23 pairs line up, the homologous pairs, because we're separating homologous pairs. They are duplicated. So if you see here, the chromosomes are duplicated. So there's sister chromatids. And one other thing I need to point out, does anybody have a blackwood marker? No? That's all right. So if you have a look, that the sister chromatids are not identical. What we talk about later on in the lecture, we talk about crossing over, where chromosomes of non-sister chromatids can actually exchange DNA between each other.
Perfect.
Yes. So what's happening is that no, in metaphase, okay?
Oh, metaphase.
Yes. So this process of crossing over happens, okay? And this is where you get genetic variation. That's why we have, you know, not everybody identical, because of this crossing over is one of the process. Another process that happens in metaphase is what we call independent assortment, where the chromosomes can line up, you know, this way, or they can the other way. This gives, So if you have 23 of those, and you can have 23 to the power of 2 to the power of 23, I think it is. I don't know what that is. That's
Big number.
8 million, I think. Can somebody do the calculation?
Yeah.
So it's a big number. The number of variations that you can have just by independent assortment.
8 million.
2 to the power of
8,608.
So 8 million, around 8 million?
Yeah.
Around 8 million different combinations that you can have by sorting 23 chromosomes. Okay? So there's a huge variation just from independent assortment, that process. Now you have a look at here, if we compare that to mitosis, in mitosis we see, let me see if there's a comparison here. No. In mitosis, you see, you get alignment of the 46 chromosomes, okay?
Yeah. Identical.
And the metaphase plate in the equator, okay?
Mm.
In meiosis one, the homologous pairs line up, because remember, we need to get to 23 chromosomes. We need to get haploid cells. So in meiosis one, what's happening is that you get separation of the
Homologous pair.
homologous pairs, okay? So that in mitosis, you get separation of what? Sister chromatids, okay? Here, you're getting separation of homologous pairs. So by the end of meiosis one, you end up with n number of chromosomes, okay? So this is now haploid. And in meiosis two, what happens is that it's similar to mitosis. You get separation of sister chromatids.
Oh.
In this case, they're non-identical. In mitosis, it was identical sister chromatids, okay? Because we got crossing over, remember?
So basically, like meiosis 2 is not identical.
Non-identical sister chromatids separate. Here, homologous pairs separate.
And mitosis identical.
Yes.
Chromatid.
Yes. So the phases are still the same. You know, you get the nuclear membrane disappearing, the centrioles going to the poles, the formation of the spindle fibers, attachment of the spindle to not to the kinetochores or the centromeres of individual chromosomes, but homologous chromosomes. Okay, in meiosis one. In mitosis one, the centromeres are connected to the spindle fiber. In meiosis two, to the individual chromosomes. Okay. So let me just go through this one by one, and hopefully we can understand it. Meiosis is usually referred to as reduction division, because what's happening is that you're reducing the number of chromosomes, okay, in the division. Finally, you come to 23 chromosomes instead of 46. So that's why it's known as reduction division. So the number of chromosomes is halved. So from diploid to haploid, we call that reduction division, okay? So the gametes, remember this term gonads?
Yes.
Gonads is a collective term referring to the testicles or testes and the ovaries, okay? So gametes, which are the sex cells, okay? So the sperm and the egg are produced in the gonads, okay? So the sperm is produced in the testes, while the egg is produced in the ovaries, all right? So so the number of chromosomes is 23. So after an egg is fertilized by a sperm, the number is returned back to diploid, 46. So after fertilization, we get diploid number. Okay? And that's why we need to have haploid. Otherwise, if we didn't have it, every time that you get fertilization, the number of chromosomes is increasing. It'll be a disaster, you know? You will end up with, after so many generations, maybe the cell won't be even viable, okay? So that's why we reduce the number and then come back to the original. So the other process that's happening during meiosis, we're getting a mixing, okay? So this is crossing over, where non-sister chromatids cross over the DNA. And I'll talk about that process in more detail when we get to it, okay? So that was the crossing over. This mixing is referring to the crossing over, okay? The reshuffling is the independent assortment. Remember, the chromosomes can line up this way or this way, okay?
Yes.
So that's what's known as reshuffling, and that number, 8 million, okay, different combinations we can get just by 23 chromosome pairs. The other thing is that the number of chromosomes is reduced, okay? So you get haploid number of chromosomes. And the difference is that these cells that we get are not genetically identical. So all the 4 cells that arise from the single cell in meiosis, so we start with a diploid cell and end up with 4 haploid cells that are not genetically identical. Whereas in mitosis, you got the same exact DNA copy in all the cells. So the trillions of cells that in your body that came from the single zygote are genetically identical, while the gametes that you produce are genetically not identical, okay? So as in mitosis, before we enter meiosis, there is a duplication of the DNA. So we get the S phase, normally DNA is duplicated, so the chromosomes become duplicated, okay? So they're unduplicated, you get duplicated chromosomes. So all 46 chromosomes are duplicated, okay? Before meiosis begins. So in meiosis 1, we got all the phases, okay? And we call them according to, we put a number. So for meiosis 1, the phases will be prophase 1, metaphase 1, anaphase 1, telophase 1, and cytokinesis, okay? So this is where you get the separation of the homologous chromosomes, okay? So you see here, homologous chromosomes separate, not sister chromatids, okay? In meiosis 1. And also we're getting that reshuffling and crossing over happening in this meiosis 1 as well, okay? So in meiosis 2, there is no interphase between meiosis 1 and meiosis 2, okay? So as soon as meiosis 1 happens, the cell undergoes meiosis 2, okay? So there's no interphase between the two. So similar steps, prophase 2, metaphase 2, anaphase 2, telophase, and cytokinesis. So here, we're getting separation of the sister chromatids, okay? The non-identical sister chromatids. Any questions so far?
Doctor,
Yes.
what is the responsible for sexual reproduction? Meiosis or mitosis?
Sexual reproduction is meiosis. Asexual reproduction
Because
is...
they are mentioned in mitosis, the same.
Yeah, it's asexual.
What is asexual?
Asexual means it doesn't need a partner, okay? So an organism dividing into two, like amoeba or something, all right? This is asexual bacteria, yeah. Asexual reproduction, okay? If the organism requires a sperm and an egg, sexual reproduction. So they can't, it goes meiosis and through meiosis, okay?
So mainly and meiosis.
Yeah, it's meiosis. So sexual reproduction is different to X. Asexual means it needs one partner. Sexual needs pairs, male and female. Okay, so let's go through meiosis 1, as I mentioned. In prophase, as in mitosis, you get the chromatin condensing to form chromosomes because, as I mentioned before, chromosomes can be easily separated. They're nice units that you can separate, while chromatin is all over the place. You can't separate it well. So you get condensation of the chromatin into chromosomes. You get, like mitosis, you get the formation of the spindle fibers, the centrioles moving to each pole, okay? The nuclear membrane disappearing, okay? And here you're getting crossing over. So actually the crossing over happens when the homologous pairs are coming together in prophase, okay? So I'll talk about crossing over later on, or here, sorry. So you see here, these are homologous chromosomes, okay? Remember, homologous chromosomes contain the same genes in different versions. So you get from your different parents, from the mother and father. So this chromosome came from your father, this one comes from your mother. They have the same genes but in slight different variations. Now, during crossing over, we can increase this variation by exchange of DNA, segments of the chromosomes between homologous chromosomes. So you see here, you got, say this is from your mother and that's from your father. At this point, you can get exchange of DNA between the two. So now, this chromosome is completely new in this here. You see that? It has a part of the homologous pair from your mother. So now, this chromosome no longer looks like the original one. Because now there's some, what's happened is mixing of the genes. So we got completely different chromosome to the original one. The same here. Okay? So this is what crossing over is. Now it's happening between non-sister chromatids, okay? So remember that. Non-sister chromatids, okay? That's what non-sister chromatids are. These are sister chromatids, okay? Those two are non-sister chromatids. So if you had exchange between these two, nothing's gonna happen, okay? It's the same exact copy because there was DNA duplication, remember, in the S phase? So the exchange has to happen between non-sister chromatids, okay? You got that?
I didn't get the part. Very nice.
You remember I said before meiosis begins, you get duplication of the DNA.
Yeah.
So the chromosomes are duplicated. Exact same copy on both of them, okay? Both sister chromatids, they're identical.
Okay.
The homologous pair, it has non-identical, they're non-identical sister chromatids,
Yeah.
okay? So each, when you compare the two homologous pairs. So the exchange is happening between non-sister chromatids,
Or non-identical.
okay?
Okay.
Because if it happens here, it's going to be the same thing.
Nothing
They're
will-
the exact same thing.
Okay.
The crossing over has to happen between the homologous pairs.
Okay.
So that's why it says non-sister chromatids, okay?
Okay.
You got that?
Yeah.
What is the process for the name of the process?
Crossing over,
Crossing.
okay? That's the name, that's what's happening, crossing over. So when we do that, now we get a new combination of genes, okay? With different, so before, you had your mother's, say, chromosome. When it crossed over with the father's homologous chromosome, and you ended up with a chromosome that is no longer identical to your mother or your father, okay? So this is adding genetic variation. So it increases the genetic variation in the offspring. So we don't look like our parents, we don't look like our brother, unless you're identical twins. In that case, you will look exactly the same because you have the same genetic material. Identical twins, they actually came from the same zygote. So it just splits into two. Sometimes it happens and forms two babies. It's not actually two separate eggs, identical twins. It comes from the same zygote. So during mitosis, sometime and usually during cell division, the zygote actually splits into two and then forms two new babies instead of the one. So that's why you get identical twins.
What about
Non-identical, they come from two different eggs and sperm. That's why they don't look the same. Sometimes they can be male and female. I actually have twins, one boy, one girl. No, obviously they're gonna be non-identical because they have different genders. They came from
Another
egg and yeah. So it's not. So identical twins come from the same zygote, from the same egg and sperm.
That means the crossing over makes the differences.
Yes, but once the egg is fertilized, there's no crossing over happening then. Okay, so if it splits into two, it's going to have the same. It's after the egg is fertilized, it's mitosis. Okay, remember that?
Yeah.
Meiosis is finished.
they must have the same sex.
Yes, of course, they arise from the same zygote. Impossible to have identical twins with two different genders, okay? They must be the same gender. Alright, so crossing over is very important for genetic variation. Otherwise, over time, mutations can cause lots of problems. If you don't have genetic variation, new variables, this is very important in adaptation to environments, mixing of the genes. Well, not evolution, as I would say. This is not evolution. This is a normal process that is happening. It's important. Okay, that's why they don't allow in our religion marriage between sister and brother or mother and father, because it can damage this DNA pool. That's the reason you shouldn't marry, because inbreeding can damage the DNA pool, and you can diseases can increase. Okay, so the marriage between blood relatives, that's why it's prohibited in our religion. In a lot of the countries, in Western countries, they don't allow it, but they still do it. Those people, and there is cases where there's inbreeding. In America, I think there was, and they found that children were very retarded, they were disabled, so inbreeding is not good, okay?
Also between cousins.
No, cousins is...
It's okay, but still,
Yeah.
there is a chance.
So much.
There is a chance. More chance than...
Yeah, but cousins is not that big of a problem.
But
There
have
is
more
a chance,
than
but
the
there is a
other.
chance, but if it's brother and sister,
More.
mother and father, that's not. No. Daughter and father, brother, son and mother, these sort of things can cause problems, okay? Alright, so as I said, in meiosis 1, in metaphase, the homologous pairs are lining up, so we got the crossing over. Now we got another variable. We got independent assortment, okay, of the homologous pairs. So you got the equator here, or the metaphase plate. The chromosomes line up independently of one pair to the other, okay? So there's no reliance on the second pair, how these two line up, okay? You see, this one can line up this way, or it can line up the other way. This one, the other way. So when we do the probability, we find that we got how many different variations? 8 million, okay? So 8 million different variations we can just get by that. Then you combine that with the crossing over. It's going to increase genetic variability. Then you're going to combine that with the 300 million sperm that are competing for one egg. So, the genetic variation is compounded every time. So, in meiosis 1, the homologous pairs line up and separate, okay? As in mitosis and anaphase 1, the homologous pairs then are pulled towards each pole, so separating the homologous pairs, okay? Then you get telophase 1 and cytokinesis, so you get the reverse of prophase, remember? The chromosomes decondense, the nuclear membrane reappears, and you end up with two non-identical haploid cells, okay?
What happens in the anaphase?
You just get separation of the non-homologous. So you get lining up of homologous pairs, and you get the separation of homologous, basically separation, yeah. So you get to telophase, you're getting the reverse of prophase, okay? So DNA is decondensing, you get nuclear membrane reappearing, you get the cleavage farrow, cytokinesis separates the cells into two non-identical cells, okay, which are now haploid, okay? They have 23 duplicated chromosomes, okay?
They're not haploid.
They're haploid, okay? So these cells are now haploid, okay? After meiosis 1, you get haploid cells. So 2 haploid cells. And as I mentioned before, that there is no interphase between meiosis 1 and 2, so you get straight into meiosis 2. Because we still have the chromosomes duplicated. Okay? We got a duplicated site, we need to separate the duplicated chromosomes. So meiosis 2 is similar to mitosis. Now you don't get lining of the homologous pairs, you get lining of the sister chromatids, okay? So we get, as I mentioned, for meiosis 2, we put the 2 number, the Roman numeral 2 after it. So prophase 2, metaphase 2, anaphase 2, similar, okay? Except here we're getting separation of sister chromatids, okay? So you see here, we're lining up sister chromatids. Are those sister chromatids identical?
No.
No, non-identical. So the result is that we get 4 haploid cells now that chromosomes are unduplicated, okay? Non-identical haploid cells. 4 cells. So they're genetically different. While in mitosis, we end up with 2 diploid cells that are genetically identical, okay?
So doctor, so in prophase 1 and prophase 2, metaphase 1 and metaphase 2, they're the same thing?
No.
1 and 2?
See, the difference here is that anaphase 2, and what's happening is that you get separation of homologous.
In the
See, you get
anaphase.
separation of homologous, okay?
Okay.
Yeah? Here you're getting separation of sister chromatids. So that's the difference.
So basically,
By the end of meiosis 1, you end up with haploid cells. But they still have the duplicated chromosomes. We need to separate them. So you get another division which separates the sister chromatids, okay?
so it separates the 2 haploid cells.
Yeah, so in meiosis 1, we get haploid cells. Meiosis 2 separates the duplicated chromosomes, so the sister chromatids, okay? So in the end, you end up with 4 cells containing 23 chromosomes, single chromosomes, not duplicated.
And doctor, for the meiosis 2, prophase 2,
Yeah.
is there a crossover?
No.
No?
It only happens here. Crossing over happens between homologous pairs. You don't have them anymore here.
So in prophase 2,
Yeah.
only the
Yeah.
the chromosomes are condensed.
Crossing over happens between homologous pairs because what's happening is they brought so close to each other.
Okay.
Okay, they held together that it allows the exchange of DNA between homologous pairs.
So what happens in prophase 2?
Prophase 2, you just get the sister chromatids lining up like this, so separating. So basically, what's happening is the nuclear member disappear. Okay, the chromosomes reform, and then you enter metaphase 2, which line up the sister chromatids. Okay. So that's the most important part, okay? There's no crossing over here, okay? Because you already separated the homologous pairs in meiosis 1.
So the important part is that in meiosis 1, it's the homologous pairs.
Yes.
And meiosis 2 is the non-identical sister chromatids.
Yes. So in the end, you end up with 4 haploid cells that are not identical. But you already reduced the number in meiosis 1, okay? Meiosis 2 is there to separate the duplicated chromosomes, okay?
Okay. So separate the duplicate.
Yes.
Okay.
The non-sister, the non-identical sister chromatids that you have now because of crossing over.
Okay.
Okay. Let's see. We've got a video here. We'll play the video and see we can play. Yes.
These are sisters.
Yes.
So not this thing.
They don't cross over. They got the 2
No,
chromosomes.
no, I don't talking about the chromosome.
Yeah.
I have no chromosome.
Yeah.
These are sisters.
Yes.
This one or this or they all.
The 2 chromosomes, single chromosome lined up together. Okay.
Okay.
So 2, they called sister chromatids. Okay. If
So
they are
this-
identical,
they all
then you have
one is-
another the homologous pair with the sister chromosome, okay, they come in exchange between each other, the non-sister chromatids, okay?
Just want to make sure. These are sisters, right? This is the next one. So, okay, so these are not sisters. These are sister chromatids. Okay. You can say this sisters and this sisters. This is one chromosome. This is another chromosome. There are two sister chromosomes. This is joined in the center. The center.
A cell that undergoes mitosis produces daughter cells that are dramatically different from the daughter cells produced by a cell that undergoes meiosis. Let's compare these two processes, beginning with a look at mitosis and meiosis one. In both mitosis and meiosis one, cells began with replicated chromosomes, each cell having 2 chromatids per chromosome. In meiosis one, the homologous chromosomes pair with each other and come to the middle of the cell together. In mitosis, the homologs move independently of each other. In mitosis, the chromatids separate. In meiosis one, the homologs separate. In mitosis, a diploid cell divides to produce genetically identical diploid cells. Each cell contains 2 complete sets of chromosomes. In meiosis one, a diploid cell divides to produce genetically unique haploid cells. Each daughter cell now contains just 1 set of chromosomes. Meiosis one is known as a reduction division because the outcome is a reduction of chromosome number. These 2 cells are daughter cells produced from meiosis one. Let's use just one of them to compare meiosis two to mitosis. A cell entering mitosis is diploid with 2 complete sets of chromosomes. A cell entering meiosis two is haploid with just 1 complete set of chromosomes. In both cells, each chromosome has 2 chromatids. In both mitosis and meiosis two, the chromosomes migrate to the middle of the cell. Then, the sister chromatids of each chromosome separate to form independent chromosomes. In mitosis, a diploid cell divides to produce genetically identical diploid cells, each with 2 complete sets of chromosomes. In meiosis two, a haploid cell divides to produce genetically unique haploid cells, each with 1 complete set of chromosomes. If we consider that meiosis two actually began with 2 cells, then the result is 4 genetically unique haploid cells. In both mitosis and meiosis two, the division is not a reduction division. Only in meiosis one are the number of chromosome sets divided by half.
Okay. Can you get your Kahoots out? Let's play some Kahoots. We've got something here for you. Did I play the mitosis video before? Mitosis, I played it?
Yeah.
Or not?
You said you'll put it in Blackboard.
Yeah. I haven't done that yet, but I'll do it.